Okay, welcome everyone to this talk, which should be called Memory Circuit Design versus Memory Circuit Designer. You will see during the talk, in which I will try to ask you also questions. So if you could please participate and raise your hand and participate to the talk. Thank you so much. So a little bit about myself. My name is Dan. I have a master's degree in electronic engineering, and I'm a fellow at Micron Technology, and I work in Folsom, California. I work in a group which is called Pathfinding Team, and we do many different types of memories, and we try to understand if that type of memory could be a good solution for Micron. And so I've been working, and I worked on different memory technologies like DRAM, so dynamic random access memory, ferroelectric RAM, HRAM, memory, MRAM, magnetic RAMs, PCM, and NOR flash at the beginning. I kind of work more on very close to the array, so I like working on sense amplifiers, whatever is surrounding the array, word line drivers, and anything like that. And as a fun activity, I do like water sports and biking. And I was a member here at the ISSCC for a couple of years. Okay, a little bit about Micron. So Micron has been founded in 1978, and a few years later, they shipped the first 64 kilobyte DRAM. So today we are buying 6 gigabyte chips. So on the same chip, now we are essentially printing 100,000 more transistors and memory cells than that in 1981. So, and you can see the evolution here. Also in 2010, Micron acquired Mnemonics, which was a joint venture between Intel and ST. So Micron also operates through acquisitions. And the two main memory types that Micron does is DRAM, so dynamic random access memories, and NAND, which is a configuration of type of floating memory device. Also, Micron produces SSD and different multi-level NAND cell technologies in 2018, and most recently, the AI narrative came, and we are selling something which is called HBM, so high bandwidth memory devices, okay, or chips. Where memory are used, here there is an example. On the left, you can see a typical graphic card or AI engine where the GPU is in the middle and there are memories all surrounding the GPU. They have to be very close to the GPU in order to guarantee the maximum bandwidth. And also, Micron, or we do, we provide solid-state drives that you may have in your laptop, in your PC, and they do have these shapes, so they are solid-state devices. And Micron produces also DRAM devices and DIMMs, which are used for, again, as a random access memories for your laptop and PC. But memories are everywhere. They are literally everywhere. You have it in the watches, phone, car, refrigerator, anything that has some sort of digital functionality probably has a memory inside. Okay, so let me tell you a little bit how a project goes. So what is the sequence that we usually employ in creating a memory chip? And this can be valid for not just for memories, but for everything. But this is what we have. We have a project start phase, a feasibility study analysis where we are trying to understand if what we want to do is actually feasible. Then there will be a first design. Someone finds a problem, someone finds a solution, someone finds another problem, and we find another solution and go on like this for many, many times. At the end, there is a validation period in which we don't find very big roadblocks, and we are trying to validate all the functionality of the memory and the logic based on the spec that we have. We have to provide a specification to the customer and the customer has to rely that we are going to meet all the specifications. So in this phase, we are doing that. We are verifying that the specifications that we gave to the customer are met. And then there is a project end. And also, there are two different approaches. I hope that it's going to be a little fun for you. say the standard approach that you may have or you may use in order to complete a project, and there is a something that I hope you will employ at the end at the end of this talk. So the standard approach is this: the project starts, feasibility, first design, problem, second design, problem, we find a solution, validation, and the project ends. Okay? Go and celebrate with your team. I hope that after this talk, you're going to approach the different phases like this. Project starts, feasibility study, first design, first setback, no problem, we are going to find a solution for sure. Second design, second problem, no problem, we will find a solution. Solution found, validation, project ends. Okay? This is what I hope. All right. Okay, so now I think I need a little bit of your help, and I would like to pretend that you just applied to a Micron position, you have been hired, and now you are a memory circuit designer, and you go to your supervisor, and the supervisor asking you, so what I should work on? And your supervisor says, well, you have to work on the sense amplifier for the next project. Here there are the two approaches and the two ways of trying to solve and to fulfill your mission and your objectives. So one is this: I just do what I've been told from my supervisor, and this is going to be the result, I believe. Instead, if you take ownership of your design and you feel like that's yours, I have to make it work, this is going to be what your approach, and you're going to be happy throughout the entire project. Okay. But before going in trying to understand what the sense amplifier does, which actually is connected to the cell and is trying to amplify the very small signal that comes from the cell to a logic value, so a full one or a full zero, you have to understand fundamentals. At least that's my approach. I like to understand fundamentals first. And in order to understand fundamentals, you have to go to the root of the problem, to the very core of a memory cell. In this case, we have to do a DRAM chip. So we have to go and look at the DRAM cell. This is a simple circuit. It has only one transistor and one capacitor. The transistor is access transistor, called AT, for example, and the storage capacitor, which is called CS, just to make it brief. And we have to identify all the nodes around here such that we can talk later and describe them a little better. So the word line here, the digit line, the plate, and the memory node here in the middle. So I listed all of them here, so you can see them here. So now I have to ask you a question first. You saw that the plate voltage here has been defined as a fixed voltage. And say that we use 1 volt for the memory node for the 1 and 0 volts, so ground for the memory node for a 0. So we store 1 volt for the 1, 0 volts for a 0. And the plate has been defined as fixed voltage. What would you think the best possible plate voltage would be? So if you please can raise your hands. So who says 1 GND? Okay, couple of hands. VCC divided by 2. Good. VCC. Okay, so VCC divided by 2 wins. And I have to say this. This is better for some reasons and maybe not perfect for other reasons. There is no correct answer. Always there are only pros and cons for each possible solution. And you will see it also later. There is one major problem, though, in DRAM, which is the oxide thickness for the storage capacitor, and that overwhelms everything else. And at the present time, it overwhelms any possible other benefits of choosing something different than VCC divided by 2. So if you choose VCC divided by 2, if the memory node is 1 volt, you have across the oxide that's in here, 0.5. If you store 0, it is negative 0.5, but the electric field is still 0.5 volts. Okay, so thank you for participating. All right. Also, before sensing the cell, we need to write the cell. We have to store something in the cells, and I hope here I will try to explain how we write and we store bits in a memory cell. Sorry, okay, and and we kind of do like this. So somehow, somewhere before the starting of this diagram, which x is time and y is volts, we raise the word line to some value, and then if we want to write a 1, so we want to pass 1 volt, we raise the digit line to 1 volt, and then the digit line is 1 volt. If the word line is high, the access transistor is on, so some charge will be moved from the digit line that we are forcing to 1 into the memory node. So the memory node will be 1 volt eventually. And then in order to store that value, to save that value, we just need to turn off the access transistor, lowering the word line. So the word line goes down, keeping a little bit the digit line again high for being sure that we are not creating any disruption in the memory node voltage. And then when it is fully down, we can lower the digit line to the plate, back to the plate value. And that is possible now because the access transistor is off. So it's like an open circuit, and we are saving something on the memory node. And this capacitor represents our memory. It has memory. The charge stays there. Only leaks out through some leakage. The same goes for the 0. Instead of setting to 1, we are setting to 0, and we are doing the same sequence. But as you could see, here the word line went higher than 1 volt. And the question for you is, you know why the gate may need to go higher? Please go ahead.
Is it because of the threshold voltage of the NMOS?
Perfect. Yes, thank you. So the word line needs to go higher than 1 in order to be sure that we are going to pass fully the 1 volt. Okay, thanks. Okay, but now we are starting to see how we are sensing the cell, we are reading the cell back. So what we do is at a certain point we want the data that we stored before back and given that to the user. And again, this access transistor was floating, and we need to, and for example, we are reading a 1. The memory node was 1 volt. The digit line starts at the plate voltage, which is 0.5. When we turn on the word line, this transistor turns on. There will be a charge sharing between the storage capacitor, so CS, and the digit line capacitance. And you will see the digit line value, which is the blue node, which is going to be routed outside onto the sense amp. You will see it later, going up a little bit. It doesn't go up that much, just need to go up a little bit in order for the sense amp to detect that. Okay. The same goes for the 0. When we sense a 0, the word line goes up, and the digit line deflects a little bit down due to the charge sharing between the storage capacitor and the digit line. Okay. But we said before that we are actually selling gigabits or gigabytes of memory, so we have to put so many DRAM cells one close to the other. And one way to do it is creating arrays. So the word line is called a word line because it's horizontal typically, so it's kind of writing words. It's a word line, and we have digit line or bit line. They're kind of used interchangeably. We assemble so many cells together, like gigabits of information in one single array. And we do this in order to create compact layout and compact memory. Okay, so let me talk about 2 possible different configurations for arrays. This is one of them, and how we connect arrays to the sense amplifier. Now we are going to creep a little bit into your goal, so try to design a sense amplifier. Say that we have 2 arrays, 2 big arrays like we defined in the previous slide, and we connect them to a battery of sense amplifiers. And we have 2 separate arrays, one on up, down, or left, right, it doesn't matter. And the sense amp is in the middle. And for example, as you can see, this sense amplifier 0 is connected with a digit line 0 reference or bar on one side, and the same sense amplifier is connected to a digit line 0 on another array. And this configuration is called open bit line, because this is not actually true. So one array is one on top of the others, and the bit line are continuous, but this is just a schematic. The schematic works like this. And since they are not in the same position, exactly in the same position, you saw in the previous talk that there could be some variabilities due to non-locality. So they're not exactly in the same place, so there may be variability just to the fact that they're slightly, one not exactly close to the other. And this configuration of open bit line has a little bit more variabilities, but it has, say, a compact area, because this is a true array. We can print this very efficiently. So there is another configuration, which is the folded bit line. And just for my convenience, I drew it like this, but it is much denser than this, so, which has less variations, because as you see here, the sense amplifier connects to two adjacent digit lines, and any possible capacitance variability on this digit line is matched better on the one very close to it, instead of into another place. So this matches a little better, but it has some kind of area cost, or at least we believe that this configuration has a area penalty, and that's it. It's just a matter of cost and evaluating the two solutions when you are building a chip. Okay, so let's go back to the previous configuration, which is the open bit line, and let's see how a sensing operation is performed. So we have one reference array on this side and one active array on this right side, and we turn on one word line at a time. So this word line goes up, and all these cells are selected. All these cells are going to share something with the digit line, all these capacitors. And what you would see is something like this in time. So the digit line bar starts from the plate, as does the digit line. But the word line at a certain point will go up, but will not go up here. So on this side, the digit line bar will remain fixed. On this other side, when the word line goes up, you may have a slightly deflection up or a slightly deflection down, depending on what's included in what's contained in the cells. And they will deviate a little bit from the center point. And also this signal is the same that you have with respect to the digit line bar. And at this point, your sense amplifier has to do something. It has to detect this small signal and amplify it to the rail in order to provide a 1 or a 0. Okay, so this is how a basic sense amp works in DRAM. This configuration, I believe you may know it well. It's just two inverters, one feeding the other, so it's a latch. And but it has power supplies in this case. Power supply switches, this one and this one. And also it has two additional switches which are connected to the digit line and to the digit line bar, as you saw in the first talk. Yeah. So the sequence that we use to activate the sense amp is like this. I just said in the previous slide, but I'll try to repeat it here with the circuit now. Digit line and digit line bar are starting from the plate again. And in idle mode, meaning we are not selecting yet that piece of array, these two switches are on, and we are forcing the digit line and digit line bar to the plate. Here, plate goes through here, goes to bias the digit line. So the digit line is fixed, digit line bar is fixed to the plate, 0.5 volts. Then let's see how a sensing operation now works. First of all, we have to release these switches, open them up such that the digit line and digit line bar now are floating and they can move. The word line is brought up, and there is a charge sharing between the cell that you saw before and the digit line. So the digit line will deflect up a little bit, for example, for a 1, and 0 for a 0. And the digit line bar will not move, so the digit line bar will remain fixed at 0.5 volts. At this point, after a little bit, when all the charge has been extracted from the cell, you can turn on the power supply of your sense amplifier, and the sense amplifier will hopefully amplify that signal in the correct direction to the fully 1 volt or fully power VCC here, and the digital line bar will go on the other direction because this is there are two inverters feeding each other, will go down to 0. And at that point, you have a full bit on your local sense amplifier, on your sense amplifier here. And this is thanks to a positive feedback loop due to the latch configuration. So one inverter feeding the other one. Okay. So now I think you saw the fundamentals, and my point is that up to now you have been a memory circuit designed engineer. So you did investigate whatever all the other design engineers did in the past. You understand the fundamentals, and now you can become a memory circuit designer and give your contribution to the team. Okay? And of course, if you take ownership of your design, you're going to be happy, or you're going to be successful, I think. That's my opinion. Okay, so let's try to frame your problem. You have been assigned to work on the sense amplifier for the next project. And here there are conditions for, here there is a basic circuit that you can take as a reference, the previous project condition, and your new condition. These are your new conditions. You have to work with this one on the right. So the circuit, the simple circuit that you can use to make your judgment is this one. So you have a cell, memory cell, 2 digit lines with some capacitance. You have a sense amplifier, and a sense amplifier offset that you can justify with the previous talk that you saw. There are variabilities, statistical local variabilities, even if the two sense amps are one close to the other, they're different for statistical reasons. Okay, so this is the circuit that you have to work with. And the previous project was like this. The voltage that we used was 1 volt, so the memory node was able to go from 0 to 1 volt. The plate was 0.5. The storage capacitor was 20 femtofarad. The digital capacitance was 80 femtofarad. And if you run a little bit of math, I didn't put voltage here, but I mean you do memory node voltage minus plate voltage times the capacitance. This is a voltage divider. Okay? You can calculate how much signal do you have. And with signal, I mean initial signal, which is the difference, is the digital deflection when you turn on the access device. So the digital deflection, call it signal, was in this case 100 millivolts. And the sense amplifier offset was 75 millivolts. So you add 100 millivolts, you have to subtract the variability, the maximum possible variabilities. Let's assume that this is so many sense amplifiers you have, you will know this. And what's remnant is 25 millivolts. It's not much, but it's positive, it's green. The project did work. There is some margin, it's okay. Because you are subtracting all the sense amplifier statistic. And that's good. So let's look at the next project. That's your assignment. And now we have the same voltage, same plate voltage. The storage capacitor capacitance reduced because it's reducing now because we want to shrink the cell. We want to make it smaller and smaller and smaller all the time. And the digital capacitance also reduced for the same reason. If you calculate the signal here is 75 millivolts in this example. But the sense amp offset didn't change because we didn't change the circuit. And the margin is 0. And that's not enough. That's not okay. Because some sense amps will fail. And we don't want that. We don't want to give the user a wrong bit. Okay? Okay, so now I think I need a little bit of your help again. And we said you are a memory circuit designer working in Micron, hopefully. And I would like you to try to solve the problem and try to find a way to make this new project working again. Okay? So you can do that alone, but I suggest you to do it in team, either with your neighbors right now, and you can even search the web if you want, because this is industry, it's not school. So this is industry. You just need to solve a problem. You can work with your colleagues. You can search the web. You can use all the legal ways to try to solve the problem. Okay. So why don't you try and you try to guess what you can do? And just for help, I put here the formula of the margin, which is this. So please, 1 minute and think about that. That's good. Okay, I think it's 1 minute. Okay, so thank you. I think 1 minute was enough. Again, there is no right answer. This is not school. Every answer or every solution you might have had should be analyzed and see if that works or not. So, and I will not ask questions. I'll just try to make hypotheses based on this formula. Okay, so let's assume that you might have thought we can reduce the digital line capacitance. That's one way. It works. We can increase the CS value. That works. We can design a lower offset sense amplifier. Instead of having 75 millivolts, have less. It works. We can increase the voltage. It works. And this is the formula. But each of the solutions has pros and cons, and since you have been assigned that task to work on the sense amp, it is your responsibility, I believe, to work on your solution and prove and analyzing cost and benefits before proposing the change to your design team. So you should look at that, and when you are reasonably comfortable and sure that you did your homework, you can propose your solution. And again, you own your piece of design, so it's your responsibility. At least that's my approach. Okay, so let's try to make an example of how to analyze your solution. Say that you said, reduce the digital line capacitance. That works, and here there is a table that tries to show pros and cons of each possible solution that we listed before, and it is just a qualitative assessment in this case. I don't have numbers, but it's just a quality assessment, but it is something. So let's call it digital line change. Okay, the power is probably better because those digital lines are going up and down all the time, so lower capacitance is less power. The cost may be a little worse for different reasons. One could be process cost. You asking the process engineering to change something in the array, in the process, and that may cost a little more. Or you want to do the digital line, make the digital line shorter, but that means adding more interruption in the big array, and that costs a little bit of area. Performance is probably going to be better because less capacitance is going to be faster to switch. The complexity is probably very similar or the same, and the margin, of course, is better. The same goes for the storage capacitor value. You're asking an increase on that. If you ask that, the power will be slightly worse, same, slightly worse. The cost may be worse because the process cost of creating a bigger capacitor requires engineering and may require more steps. So it's a little worse. The performance is probably the same because or similar, because the storage capacitor is not as capacitive as the digital line, which is the main capacitance that we have to switch all the time. The complexity is probably the same as far as the design is concerned, and the margin is better. So designing a low offset sense amplifier, and when I was writing this evaluation, I had in mind something like an offset cancellation technique, which I'm not going to show here, but just think about that. And offset cancellation technique may require at the beginning some time to do that offset cancellation. And since you need to turn on that sense amp, probably the power is a little worse. The cost may be even better because now that you are implementing offset cancellation technique, you may create those 4 transistors with a smaller area. You can make them smaller because now we are trying to cancel out that offset, and you may gain a little bit of area in some cases. The performance is probably worse due to the initial offset cancellation phase, and the complexity is worse, significantly worse for who has to design the sense amplifier, which is you. And the margin is better. Or you can increase the voltage, so the power will be worse due to the switching. The cost is the same because it is exactly the same chip, just with a higher power supply. The performance is probably better because you're going to switch capacitances faster. The complexity is the same and the margin is better. So also, for each of the possible solutions, you saw here these names here, process, design, reliability. These are probably the other groups that you have to work with in order to validate your proposal. So if you want to reduce the digit-line capacitance, you probably have to work with the process engineering. You can't work alone and just say, oh, we have to reduce it. You have to talk with another team and see if it is possible. What's the cost? How many dollars per wafer or something like that? The same goes for increasing the capacitance, the storage capacitor. For the offset cancellation technique, you have to talk with your team because maybe you need a special timing or something. You have to talk with another engineer that's in charge of another piece of the design and has to implement what you want in the sense amplifier, to control the sense amplifier. And to increase the voltage, you have to talk with the reliability team. They spend their effort trying to have as low defectivity as possible. Now you want to increase the voltage, but that has to be evaluated. Okay. So you have to work cross-functionally, even if your goal, your assignment is just that very small piece of design. Okay. All right. So here is the conclusion for my talk, which is, in order to become, in my opinion, in order to become a circuit designer, you have to first try to be a circuit designed engineer, so to learn everything that you can learn before working on your part. And there is no wrong solution. There may be different solutions. You can even use multiple solutions to solve one problem. So don't worry about saying something that you believe is not worth saying. You can say that in brainstorming sessions. If you think that your idea is a little weak, it doesn't matter. You should say that, in my opinion. But before proposing a change, you have to do your homeworks and test and prove that your solution is a real solution. And you have to try to do it fairly. So you have to look at your solution as it is not yours. Try to look at the solution and analyze everything you can about that. And don't be biased on your ideas. Try to work with your team. And the ideas coming from everyone, they are worth, in my opinion, be analyzed. You should work close to your team. That's my suggestion. So after this, I believe now you are a memory circuit designer, which is happy throughout the entire project. So thank you very much.